Hi everyone, welcome to Unit 26 of online course on probability distributions. In the last session, we have defined negative binomial distribution, its different versions of probability mass functions, and its properties related with the mean, variance, and we have derived the probability generative function and its moment generative function. And after getting the moment generative function, we have obtained a result that is known as additive property of the negative binomial distribution. All these matters we have discussed in previous two sessions. And now in this session we are going to discuss the negative binomial distribution and its association with the Poisson distribution. Or we can treat the negative binomial distribution as a limit of the Poisson distribution on the basis of certain conditions. And before obtaining that result, let us describe the probability mass function of the negative binomial distribution in another form, and that is how to establish the probability mass function of the negative binomial distribution as a general term of expression q minus p all power minus r. Note that this capital Q and capital P are defined as small letter p. Our negative binomial distribution, we have x is a negative binomial random variable with the parameter r and p, okay, and this we defined q value as 1 by p, or p is equal to 1 by q, and defined the p capital P value as q divided by p. See, either this way we can represent small letter p, that is probability of getting success, as 1 by q, and probability of failure q as p divided by q, or this q, capital Q is nothing but 1 by p and capital P is equal to q by p. Remember, we have p plus q is equal to 1. In the case of the Bernoulli random variable, Bernoulli trials, probability of getting success and probability of getting failure, P and Q, that are equal to 1. So, this is actually 1 by Q plus P divided by Q is equal to 1, or P plus 1 is equal to Q, or Q minus P is nothing but 1. So, these are the matters we have to identify with respect to the notation Q and capital P. See, our small letter p and small letter q are probability of getting success and probability of getting failure, and that are the sum of these two values equal to 1. Suppose we are representing this small letter p, that is probability of getting success and probability of getting failure q, in terms of new quantities q and p, then q and p satisfies q minus p is equal to 1. And is it possible to represent the probability mass function of the negative binomial distribution as a general term of this expansion q minus p all power r? That is our problem here. And that is, we have x is a negative binomial random variable, and as usual our probability mass function is equal to this x plus r minus 1 cx p power r q power x, where x is equal to 0, 1, 2, etc., and p plus q is equal to 1. Okay. So, this is our probability mass function. And we can write this x plus r minus 1 cx in another form, and that we expressed in the last session. That is, and this minus rcx into minus 1 power x, or combine this. So, we can represent the probability mass function of the negative binomial random variable in this form also. F of x is equal to minus rcx p power r minus q power x, where x is equal to 0, 1, 2, 3, etc. So, these are the two different versions of the probability mass function of the negative binomial distribution that we already discussed. And now our aim is how to make this probability mass function value in terms of our new variables capital P and capital Q. And remember, capital P and capital Q are defined. Q is equal to 1 divided by P, and capital P is equal to Q divided by P. And of course, and Q and P satisfies capital Q minus capital P is equal to 1. And that is, so all this matters already given here, that is our P is equal to 1 by Q and Q is equal to P by Q, and so we have established Q minus P is equal to 1, that already we have discussed. Then the probability mass function of the negative binomial distribution minus RCX, see earlier we have minus RCX P power R minus q power x is the original form of the negative binomial probability mass function we have. F of x is equal to minus RCX p power r minus q power x. Represent this function value in terms of these two new variables, that is minus RCX, this P is what? 1 by q, that is, so here it is q power minus r, and this okay, minus q is what? Minus q is minus p divided by q, so minus p divided by q power x. So, we have another form of the probability mass function of the negative binomial random variable. F of x is equal to minus RCX q power minus r minus p divided by q all power x, where x is equal to 0, 1, 2, etc. and also q minus p is equal to 1. That is important. Q minus p is equal to 1. And by looking this expression, we can see that this is nothing but it is the general term of the expansion of q minus p all power minus r, or q power minus r 1 minus pq divided by minus r, this way. So, this expression is nothing but the general term of the negative binomial expansion of q minus p all power minus r. So, remember, this is another way of representing the probability mass function of the negative binomial distribution, where this capital P and capital Q satisfies q minus p is equal to 1. Okay. And if, what is one more before going to the main problem, let me discuss the moment generative function. Already we obtain the moment generative function of the negative binomial distribution. But if we are representing the probability mass function of the negative binomial random variable in this form, that is in terms of capital P and capital Q, how do you find the moment generative function? So, what is the moment generative function? Expectation of e power tx. And that is e power sigma over e power tx. Already we have f of x minus rcx q power minus r minus p divided by q all power x, where q minus P is equal to 1. This is the probability mass function we have. And f of x is this minus RCX q power minus r minus p divided by q power x. You substitute here. And now this e power tx and this factor are powers of x. Combine these two, we can write sigma over x is equal to 0 to infinity minus RCX q power minus r. This e power tx is combined here. So, minus p e power t or divided by q or power x. What is the advantage of writing like this? This we know. See, minus RCX q power minus r p divided by q minus p divided by q power x is nothing but it is the q minus p all power minus r. So, based on this, this is actually q minus p. Instead of we have minus p by q, we have minus p e power t or divided by q. So, q minus p e power t all power minus r. So, when we are representing the negative binomial probability mass function in terms of the new quantities capital P and capital Q like this, f of x is equal to minus RCX q power minus r minus p divided by q all power x. Our moment generative function of the random variable is equal to q minus p e power t all power minus r. So, we have the moment generative function, the moment generative function is equal to q minus p e power t. See, this is our moment generative function. So, we have moment generative function of the negative binomial random variable as q minus p e power t all power minus r. Remember, q minus p is equal to 1. Okay. So, this is our moment generative function of the negative binomial runaway q minus p e power t all power minus r. Okay. So, and if it is, how do you find the mean and variance of this random variable? So, to find the mean and variance, we can make use of the usual technique of differentiating the moment generative function and put t is equal to 0, you will get the arbitrary moments. So, let me try to find the first arbitrary moment. So, expectation of x is nothing but derivative of the moment generative function with respect to t when t is equal to 0, if the function is differentiable. And if it is, what is the derivative of the moment generative function with respect to t, if this is the form of the moment generative function we are using? So, this is minus r into q minus p e power t all power minus r minus 1 into minus p e power t. So, when we are differentiating the moment generative function q minus p e power t all power minus r with respect to t, we have this expression. And when t is equal to 0, when t is equal to 0, this expression becomes minus r into q minus p, c e power 0, 1. So, q minus p power minus r minus 1 minus p. Okay. And q minus p is equal to 1. So, this is minus r into, so r into p. This is capital P. So, moment generative function is differentiating with respect to t, and substitute t is equal to 0, we have the expectation of x is equal to rp. Similarly, we can find the second moment, second arbitrary moment, and that is second arbitrary moment is obtained by R, this first arbitrary moment, that is mean is obtained by Rp, and second arbitrary moment is obtained by differentiating the moment generative function 2 times and put t is equal to 0, that is our second arbitrary moment. On the basis of the second arbitrary moment, you can find the variance by substituting in the formula of the variance. So after getting this is our first derivative, you find the second derivative of this one, and then that is our expectation of x square. You substitute that expectation of x square in the variance formula, you will get the variance that is equal to RPQ. So that is you find this value, see, we have this is equal to Rp into Q minus P all power minus R minus 1 is the value, sorry, e power t is the. This is equal to Rp e power t Q minus P e power t all power minus R minus 1. That was the first derivative of the moment generative function. You find this, use this expression to find the second derivative of the moment generative function, and variance of x is obtained by, this is our expectation of x square, you get this expectation of x square, and variance of x is equal to expectation of x square minus expectation of x the whole square, and substituting the values, this become RPQ. So mean is equal to Rp and variance is equal to RPQ in the case of the negative binomial distribution, if we are expressing that probability mass function in terms of capital P and capital Q, where capital P is equal to Q divided by P, that is capital P is equal to Q divided by P, and capital Q, that is our, this is actually Q is equal to small letter q is the, small letter p is the probability of getting success and q is the probability of failure, and so capital P is Q divided by P and capital Q is equal to 1 by P. Okay. So these are the mean and variance of the negative binomial distributions. Let me find the Coumadin generative function also. So using the moment generative function already we have the moment generative function is equal to Q minus P e power t all power minus R. That is the moment generative function, and we know Coumadin generative function is the logarithm of the moment generative function. So apply this logarithm of this expression. This is minus R logarithm of Q minus P e power t, and that can be simplified as minus R log Q minus P e power t is equal to see kappa x t, this is the Coumadin generative function, and this is equal to minus R logarithm of Q minus C e power t. This e power t is expanded, that is 1 plus t by divided by 1 factorial plus t square divided by 2 factorial plus etc. And based on that expansion, this is again p and q minus p is equal, remember q minus p is equal to 1. So based on that relationship between q and p, this expression reduces to minus R logarithm of 1 minus p into t divided by 1 factorial plus t square divided by 2 factorial plus etc. because q minus p is equal to 1. So, the combinant generative function of the negative binomial distribution in terms of the capital P and capital P Q is this expression. Again, using the logarithmic expansion log of 1 minus x form, using that one, this is written as minus r is here, logarithm of 1 minus x, that is minus x is here, this is the x, minus p, t divided by 1 factorial plus t square divided by 2 factorial minus x square by 2 etc. And from this expression, find the coefficient of t power r divided by r factorial for different values of r. And when you are finding the coefficient of r, t power r, when r is equal to 1, that is t power 1 divided by 1 factorial, you just look what is the coefficient of t divided by 1 factorial. See, this is the factor related with the t divided by 1 factorial. So, the coefficient is minus rp. So, kappa 1, that is the first combinant, is equal to rp. And you find the coefficient of t square divided by 2 factorial. Find the coefficient of t square divided by 2 factorial, and t square divided by 2 factorial, this is one of the factors, t square divided by 2 factorial, and here also t square divided by 2 factorial, this is squaring. So, this is the factor t square. So, t square by 2 factorial, that is p square, that is the coefficient is p square. Okay. So, the value is equal to rp, and this minus become plus. So, rp square. So, rp into 1 plus p or rpq. So, first component is rp and second component, of course, that is a variance, already we calculated as rpq. So, first component rp mean and second component variance, that is equal to rpq. These are the values we have already obtained for the negative binomial distribution. If we are representing negative binomial distribution on the basis of the new values capital P and capital Q. Okay. And now, on the basis of this representation in terms of capital P and capital Q, let us discuss the limiting behavior of the negative binomial distribution. In the beginning, I mentioned that the negative binomial distribution, if we are applying certain limiting condition on the base on negative binomial distribution, we can consider that distribution as a Poisson, or that is approaches to the Poisson distribution. So, this is a result related with the limiting behavior of the negative binomial distribution. A negative binomial distribution tends to Poisson distribution as p tends to 0, or you note capital P. Capital P is equal to q divided by p. Capital P is equal to q divided by p, and such that Rp is equal to lambda. Rp is equal to lambda, a finite number, and these are the conditions we are applying. So, capital P tends to 0, R tends to infinity. Of course, Rp is equal to a finite number lambda. Then negative binomial distribution tends to Poisson distribution. So, this is the result related with the limiting behavior of the negative binomial distribution. Remember, we are establishing this result based on the new variables capital P and capital Q, where capital P is equal to the ratio between probability of failure and probability of success. Capital P is equal to Q divided by P. So, this is the probability mass function of the negative binomial random variable x plus r minus 1 Cx p power r q power x. Let us change this p, small letter p and small letter q in terms of the new variables. So, this is Q is equal to 1 by P. Q is equal to 1 by P. So, so these two variables, capital P and capital Q, are like this. So, when we are substituting these two values here, small letter p power r q power x changes to q power minus r. See, this is 1 by p, so q power minus r, and q power x, that is q is our q, q is equal to capital P, and capital P is equal to q divided by p. On the basis of that, this q can be written as p by capital P divided by q power x, where x is equal to 0, 1, 2, 3, etc. And remember, q minus p is equal to 1. Okay. And then what we are doing here, so all this matters are already, the relationship between p and q already mentioned. And then f of x is this x plus r minus 1 cx is written as x plus r, see, x plus r minus 1 cx is actually x plus r minus 1 in x plus r minus 2 etc. up to r plus 1 r divided by this x factorial by cancelling the common factors. So, x plus r minus 1 cx is x plus r minus 1 into x plus r minus 2 into etc. up to r plus 1 into r divided by x factorial, that is written here, into q power minus r, q power minus r. Earlier we have q power minus r is the value, and q is equal to q minus p is equal to 1. So, q is equal to 1 plus p. So, this is q power minus r become 1 plus p power minus r. Then again p divided by q power x, that is p divided by q is 1 by 1 plus p all power x. Okay. So, that is our probability mass function. See, our probability mass function x plus r minus 1 cx q power minus r p divided by q power x, where x is equal to 0, 1, 2, 3, etc. and q minus p is equal to 1. This is modified to f of x is equal to this form, x plus r minus 1 into x plus r minus 2 etc. up to r plus 1 into r divided by x factorial 1 plus p all power minus r p divided by 1 plus p all power x. And again, this x plus r minus 1, x plus r minus 2 etc. up to r plus 1 into r is converted to, r is taken outside. So, this is actually x plus r minus 1 is r into 1 plus x minus 1 divided by r. This, and again this is r into 1 plus x minus 2 divided by r plus etc. up to r into 1 plus 1 by r into r. Okay. So, numerator value is this one. So, that is r etc. up to, this is not plus, into. So, this all r's are taken together, that is our r power x. So, this is x plus r minus 1, x plus r minus 2 etc. up to r plus 1 into r is 1 plus x minus 1 divided by r, 1 plus x minus 2 divided by r, 1 plus 1 divided by r into 1 of course, and all r factors are taken together, written as r power x divided by of course r x factorial 1 plus p all power minus r p divided by 1 plus p all power x. So, this is the final shape of the probability mass function. Okay. Then what we are doing? Now you look, f of x is equal to, when r tends to infinity, see, when r tends to infinity, suppose we are applying the condition r tends to infinity. So, when r tends to infinity, this becomes 0, this becomes 0, all factors are 0, all are 1s. So, when r tends to infinity, that expression become 1. So, okay. So, only remaining factor 1 divided by x factorial. 1 plus p all power minus r and rp divided by 1 plus p all power x, because we have r power x is there and p divided by 1 plus p all power x was there, and that are combined, we can write rp divided by 1 plus p all power x. And we have rp is equal to lambda, that is our assumption. Rp is equal to lambda. So, we have 1 divided by x factorial 1 plus this p is actually lambda divided by r. So, 1 plus lambda divided by r power minus r, rp is what? Lambda. So, lambda power x, that is, this is lambda, this is taken as lambda power x, lambda power x here, and this is 1 plus lambda divided by r power minus r, and this is 1 divided by p is lambda divided by r power x. And again you apply the r tends to infinity, the limiting behavior, r tends to infinity here also, this become lambda power x divided by x factorial, and 1 plus lambda divided by r power minus r when r tends to infinity, that is nothing but e power minus lambda, and this is 1. So, this is actually e power minus lambda when applying the limit r tends to infinity. So, f of x is equal to lambda power x divided by x factorial e power minus lambda when x is equal to 0, 1, 2, 3, etc. And we are applying the condition r tends to infinity. So, and this is nothing but our probability mass function of Poisson distribution with the parameter lambda. With this, let me wind up this session here, and thank you for listening.